Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 2 lecture. I hope you enjoy it. This is chapter 8.4, and it is Trigonometric Substitution. Right? And here we go. So this is Trig sub. In general, I call Trigonometric Substitution Trig sub. And this is for a being greater than 0. All right? This is what we have. We have three scenarios. If the square root of a squared minus u squared shows up in the integral, then what we need to do is let u be equal to a sine theta, all right, where u represents whatever function we have here being squared, all right. And notice here that if u is equal to a sine theta, that tells us then that u over a is equal to sine theta. Therefore, we get this triangle, all right. So sine from SOHCAHTOA is opposite over hypotenuse, so opposite, and this is the hypotenuse a, making the remaining side, the adjacent side, the square root of a squared minus u squared. And notice here that the a squared minus u squared square rooted showed up in our triangle. All right. If we got the square root of a squared plus u squared somewhere, what we're going to do there is we're going to let u be equal to a tan theta. Notice that this implies the triangle u over a, excuse me, this implies that u over a is equal to tan theta, which then implies the triangle as such. We have tangent is opposite over adjacent, so this is the opposite, this is the adjacent, and then the hypotenuse will be the square root of a squared plus u squared. Alright, and lastly, I'll do the third scenario. The third scenario is if I end up with the square root of u squared minus a squared. In there, u is going to be a secant theta, all right, which implies then that u over a is secant theta, and that implies this following triangle. Secant is the reciprocal of cosine, all right, so cosine from SOHCAHTOA is adjacent over hypotenuse, so that would mean that secant is hypotenuse over adjacent. So we have the hypotenuse, here's the adjacent. That tells me that the remaining side will be the square root of u squared minus a squared. And again, notice that that radical showed up in each of these triangles. Now, we have to keep in mind that u represents whatever function we have in there, all right? It's not like this is not u substitution in the normal sense. You'll see what I mean in the first example. So here we go. So this is example A. And example A says we've got the square root of 4 over x squared radical 16 minus x squared dx. All right. And in here, notice that we have our constant minus a function. So because we have a constant minus a function, well, that's the first scenario. We're going to be using u being equal to a sine theta. But in this case, our u is x, right? First, let me rewrite this a little bit. It's going to be 4 over x squared times the square root of 4 squared minus x squared dx. But as I was saying, here, our u is actually just x, all right? Because remember, up here, the generic format over here, that u represents some function of x. In this case, our function is just x. So what we're going to do now is we're going to say, well, that x is equal to a, which is 4 sine theta. Therefore, dx would be 4 cosine theta d theta. Don't forget to find the dx. You need to be able to replace it. All right. So at this point, we get that this is the integral of 4 over x was 4 sine theta. So I have 4 sine theta squared times the square root of 4 squared minus 4 sine theta squared. And then instead of the x, I have times 4 cosine theta d theta. And now, let's simplify this a little bit. All right. So on the numerator, I have, well, 4 times 4 cosine theta is just 16 cosine theta. On the denominator, 4 sine squared is 16 sine squared theta. And inside the radical, I'm just gonna, for now, I'm gonna go back to rewriting as 16 minus 16 sine squared theta. And all of this d theta. Now let's see what we can cancel out. Well, right away I see the 16s cancel out. And for now that's everything that cancels out. But let's look inside this radical. And I'm gonna do it here in yellow, just the radical. I have 16 minus 16 sine squared theta. In there, I can factor out a 16 and I'm left with 1 minus sine squared theta, which gives me, well, the square root of 16 cosine squared theta, which is just 4 cosine theta, right? So that radical just simplifies down to 4 cosine theta. And at that point, we're going to say, well, this gives us now the integral of, on the numerator, we still had cosine theta. On the denominator, we still had that sine squared theta. This radical became 4 cosine theta. And we still have the d theta left. From there, we see, well, the cosines cancel each other out. So what we really have here is 1/4 times the integral of cosecant squared theta d theta, right? Notice I wrote the sign up to the numerator as cosecant, right? So I have that cosecant squared. And from there, well, what is the integral of cosecant squared? Well, the integral of cosecant squared is negative cotangent. So I end up with negative 1/4 times cotangent theta plus c. But the problem was not about theta, right? It was not about theta. So let's see what we need to do. Recall that I said that this is going to imply a triangle. So let me copy that and bring it down to where we're working. There it is. And I'll do this in blue. So in here, this implies a triangle. So let's show which triangle. So dividing both sides by 4, I end up with x over 4 is equal to sine theta. From SOHCAHTOA, I know that sine is opposite over hypotenuse, so we end up with this following triangle. So opposite is x, the hypotenuse is 4, the remaining side would be the square root of 16 minus x squared. And we're looking to replace that cotangent. All right, so from this angle, what is cotangent? Well, cotangent is the reciprocal of tangent, right? And from SOHCAHTOA, tangent is opposite over adjacent. So cotangent is adjacent over opposite. So I end up with adjacent, the square root of 16 minus x squared, over the opposite, which was just x. And we still have that plus c on the outside there. All right. And that's really the final answer. If you really wanted to, you can rewrite this as negative radical 16 minus x squared over 4x plus c, but you don't really have to. You could have stopped at this line. But you do need to get to this line, right? You do need to put it back into terms of x because this is an indefinite integral. All right, so that was A. B. In B, we've got the integral of the square root of x squared minus 25 over x dx. All right. So that's what we've got there. Now let's see what we should do here. We've got a minus inside the radical. All right. So let's look for the minuses. We've got two options, option 1 and option 3. But if you recall, the minus that we had was a function minus the constant. So that means now we are in scenario 3, function minus the constant. All right. So over here, I'm going to start with saying, well, let x be equal to a, which in this case is 5, right? Because in here, that 25 is 5 squared. So I have 5 secant theta. So x is 5 secant theta. So that tells me that dx would be 5 secant theta tan theta d theta. All right. And at this point, well, let's see what happens. This integral now becomes the integral of the square root of x was 5 secant theta, so 5 secant theta squared minus 25 over 5 secant theta. And remember to replace the dx. The dx is 5 secant theta tan theta d theta. And let's cancel some stuff out. 5 secant theta, 5 secant theta, gone. So we still have that tan theta there. Let's make that theta look better. So tan theta. All right, so now from there, let's see, what do we have left? Inside that radical, well, what I actually have is the square root of 25 secant squared theta minus 25. All right, and well, that's not going to be over anything anymore. The denominator got fully canceled out, and I still have a tangent out here. So tan theta d theta. All right, and now at that point, we're going to say, well, what does this do? So let's look at that radical, and I'll do it on the side over here. So we've got radical 25 secant squared theta minus 25. They both have a 25, so I can factor that out. So I have 25 times secant squared theta minus 1. Secant squared theta minus 1 is tangent squared. So we have 25 tangent squared theta, giving us 5 tan theta. So what we end up with this integral, now remember, that was the entire radical. So this integral now becomes the integral of 5 tan theta, right? 5 tan theta was the entire radical here, times tan theta d theta, which gives us now 5 times the integral of tan squared theta d theta. And now let's remember how to integrate tan squared. All right. The way that we integrate tan squared is we rewrite it in terms of secant. So we have 5 times the integral of secant squared theta minus 1 d theta. All right. And again, that's from the Pythagorean identities. So at that point, we're going to say, well, the integral of secant squared is just tangent. So we have 5 times tan theta minus the integral of 1 with respect to theta is just theta. So there we go. Plus c. Don't forget the plus c. But now we need to replace these things. So let's recall what we had up here. We had x is equal to 5 secant theta. So what we're going to do here is look at the triangle that implies. X is equal to 5 secant theta. All right. Notice here that this tells us that x over 5 is equal to secant theta. So what we can say now is that if this is theta down here, well, recall that secant is the reciprocal of cosine. And cosine was opposite over hypotenuse. So in here we have hypotenuse over the opposite. But not opposite, adjacent. See what happens adjacent. SOHCAHTOA, ka. So, yeah, so the reciprocal of cosine would be secant, and cosine again was adjacent over hypotenuse, so we ended up with hypotenuse over adjacent. All right, cool. Now I said it right. Now this side over here, the remaining side ends up being the square root of x squared minus 25. So now we're gonna go back into this part over here. So we have 5 times tangent. Based off of this angle, tangent is opposite over adjacent. So I end up with the square root of x squared minus 25 over 5 minus theta. But what would theta be? So there's multiple ways to figure that out. But in here, the easiest way is, let's look at this line right here. All right. And I want to bring this down over here. Well, I guess I could have spot here. Space, I mean. From here, if I solve for theta, I take secant of both sides. All right. So if I take secant inverse of both sides. So if I take secant inverse of both sides, I end up with secant inverse of x over 5 is equal to theta. All right. So there we go. That's what the theta is going to be. So what I have now over here for theta is secant inverse of x over 5. And we have all of that plus c, right? If I distribute this 5 now, what I really have as my final answer is radical x squared minus 25 minus 5 secant inverse of x over 5. All right? So it's pretty important to remember how to build these triangles, all right? Let's do another example. So that was B. So C. And C says the integral of 9x cubed over the square root of 1 plus x squared dx. Notice here that we have a plus, right? So having a plus right away should tell you that we're working with tangent, right? So we're going to start with, let x be equal to a is 1, so 1 tan theta. Therefore, dx would be equal to secant square theta d theta. At that point, what we have is the integral of 9 times x was tangent, so tangent cube theta, over the square root of 1 plus x again was tangent, so tan squared theta, and then dx was secant square theta d theta. And now, let's look at that radical sign. Well, actually, it's really just one step here, so I won't do it on the side. 1 plus tan squared is just secant square theta. So we have the square root of secant square theta instead of that. And the square root of secant square theta is just secant. So what we can do now is we can rewrite this integral now as the 9 times the integral of tan cube theta over secant theta times secant square theta d theta. And now at this point, this secant cancels out the square, and we end up with 9 times the integral of tan cube theta times secant theta d theta. All right. And now, what I notice here is that we've got a product of tangent and secant. All right. If you recall from 8.3, when we have a product of tangent and secant, what we need to do is look at the exponents. In this case, we have the exponent of tangent is even and the exponent of secant is odd. All right. So because the exponent of tangent is even, what I'm going to do there is I'm going to split this up into the following. So I'm going to split this tan cubed into tan squared times tangent. So I have here 9 times tan squared theta times tan theta secant theta d theta. And from there, what I'm going to do is tangent squared is just secant squared theta minus 1. And we still have tan theta secant theta d theta. Now at that point, what I'm going to do is I'm going to say, well, let u be equal to secant theta. Then du would be equal to secant theta tan theta d theta. And look how convenient that is, because that secant theta tan theta d theta is this entire thing. So that's just our du. And now, at that point, well, let's see what else we can do. So u is equal to secant theta. So what we have here is 9 times the integral of u squared minus 1 tan theta secant theta d theta, that's just du. So integrating that, now I have 9 times u cubed over 3 minus u, and then that plus c. But the problem was not about u. All right? The problem was not about u. It was, what was it about? Before it was about u, it was about secant, right? Before it was about u, it was about secant. So what we can do is replace that. So we have 9 times secant cubed theta over 3 minus secant theta plus c. All right? If I distribute that 9, what I really have now is just 3 secant squared theta, not plus, minus 9 secant theta, and we have that plus c. Now let's recall what this problem was about before it was about theta. It was about x, specifically where x is equal to tan theta. So let's look at the triangle that implies. So we have x is equal to tan theta. Recall that x is the same thing as saying x over 1. So what that does, it allows us to make this triangle where this is theta, and then tangent. Tangent from SOHCAHTOA is opposite over adjacent. So in this case, the opposite is x, the adjacent is 1, making the hypotenuse the square root of 1 plus x squared. And that's from the Pythagorean theorem, right? So at that point, we can rewrite this now as, oh, look at that, I just realized I have a typo, or whatever that is. A misspell, miswrite, maybe, I don't know. So secant theta, from this triangle. Remember that secant is the reciprocal of cosine. Cosine was adjacent over hypotenuse, so what we're going to have here is hypotenuse over adjacent. So we have 3 times, and this is going to be to the third power, the hypotenuse over the adjacent. So this is the square root of 1 plus x squared. And then we have that minus 9 times secant theta. So that's just the square root of 1 plus x squared. I'll write that as 1 plus x squared to the 1 half. There we go. And then that plus c. All right. Now, the next thing I'm going to do here is, I mean, technically, that's a good enough final answer. I'm just going to simplify it a little bit further, just that it looks prettier. All right. So in here, I'm going to factor out a 3 and a 1 plus x squared to the 1 half. All right. I see here that there's a power of 1 half here, right? But then to the third, well, you know what? Perhaps I'll write it. I'll write it first. I'll write down the step. This actually should be to the 3 halves, and then minus 9 times 1 plus x squared to the 1 half plus c. All right. Now it's way more visible. We can see the 3 halves. Cool. So at this point now, I'm going to factor out what I was saying before. I'm going to factor out a 3 times 1 plus x squared to the 1 half. And what am I left with now? Well, in the first part, I started with the exponent of 3 halves, and I took out a 1 half. So 3 halves minus 1 half is 2 halves. So we have now here 1 plus x squared to the 2 halves. But 2 halves is 1, and we don't normally write 1 as our exponent. In the next part, I took out the 1 plus x squared to the 1 half, so I'm left with just 9. And then we have that plus c, right? And, sorry, not 9. It should be 3, because we took out a 3. Look at that. All right, so now at that point we say, well, 1 minus 3 is negative 2. So I have 3 times 1 plus x squared to the 1 half times x squared minus 2. See, and that looks way prettier. But anyway, that would be the final answer there. And again, we did a whole bunch of trig identity stuff in this case, all right? So you have to make sure that you recall a lot of your trig things, specifically how to build these kinds of triangles and the Pythagorean identities, whether it's sine squared plus cosine squared equals 1 or the rest of those that are derived from that. All right, so that was C. Let's do D. D is the integral of 3x squared over the square root of 4 minus x squared dx. All right, now in here, notice that we're starting with radical in the bottom of 4 minus x squared. So I have a constant minus a function, so that tells me that I want to be using sine. And in here, you should be looking at this 4 as 2 squared. All right, so we're going to have x is equal to 2 sine theta. Therefore, dx would be 2 cosine theta d theta. And now, what does that tell us? That tells us that the integral becomes 3 times 2 sine theta squared over the square root of 4 minus 2 sine theta squared dx, which was 2 cosine theta d theta. All right, let's simplify as much as possible here. So on the numerator, I have 3 times 2. 3 times 2, that's 6. So I really have a 6 all the way on the outside. What else do I have? I have a sine squared times cosine. So sine squared theta times cosine theta d theta. On the denominator, that's really the square root of 4 minus 4 sine squared theta. And now let's look at that square root, right? So in there, I have the square root of 4 minus 4 sine squared theta. If I take out a 4 but still leave it inside the radical, I end up with 4 times 1 minus sine squared theta. Now 1 minus sine squared is cosine squared, so I have the square root of 4 times cosine squared theta, which gives us 2 cosine theta. And I wrote an extra s there. 2 cosine theta. Alright. And now, we're not done. This was just rewriting the denominator. So what we can say now is this becomes 6 times the integral of sine squared theta cosine theta d theta over, and instead of that radical, we've got 2 cosine theta. 2 cosine theta. So now what we see is that the cosine thetas cancel out. The 6 and the 2 reduce to being just 3. So what we have now is the integral of 3 times sine squared theta d theta. All right. And now to figure out where to go from here. Well, we've got an even power of sine, and we have no cosines around. So technically we have an even power of cosine as well, because that power would be 0, and 0 is an even number. So in here, right? In here, the very first thing we're going to do is, or the very next thing I should be saying that we're going to do is the power reduction formula. All right, the power reduction formula. And the power reduction formula was, so I still have this 3 out here. The power reduction formula gives us that this sine squared is really 1 minus cosine of 2 theta over 2 d theta. All right. If we were working with cosine squared, then this would have been a plus. But with sine squared, it is a minus. And at that point, well, this over 2, I can take it to the outside. So I have 3 halves integral of 1 minus cosine of 2 theta, and then d theta. And at that point, we're going to say the integral of 1 is, well, in terms of theta, is just theta. The integral of cosine of 2 theta, well, the integral of cosine of 2 theta would be sine of 2 theta over 2. And then we have all of that plus c. All right. If I distribute the 3 halves, I end up with 3 halves theta minus 3/4 sine of 2 theta plus c. And at that point, we're going to say, well, we've got um, a sine of 2 theta. All right. The sine of 2 theta, there's an identity for that. All right. There is an identity for that. And the identity is quite simple. Hold on. I want to verify something. Oh no, I messed up. I just realized I messed up. Look at this. I completely ignored that too. Let's fix that. Let's fix that so you see how to fix your mistakes. So in here, this part right here was 4 sine squared theta. And I never accounted for that 4. So that 4, well, I'm going to put it out here. 4 times all of that. 4 times all of that. 4 times all of that. And here I'm going to rewrite that as 4 times 3 is 12. And when I take the 2 on the outside, that 12 over 2 is 6. And that 3 halves is not a 3 halves. It is a 6. And when I distribute that 6, I end up with 6 minus 3. Excuse me, 6 theta minus 3 sine squared, sine of 2 theta. All right, good, good. We're all caught up now. All right, so now the problem was not about theta, right? So we need to make sure that we put things back into terms of, well, x, right? Because our original variable was x. But here's an issue. We've got the sine of 2 theta. Let's rewrite that. From the double angle formulas for sine, this is, hold on, minus 3 times, so sine of 2 theta is 2 sine theta cosine theta, right? And then we have that plus c. So at this point we get, this is 6 theta minus 6 sine theta cosine theta plus c. Now let's look at the triangle that this originally implied, all right? And here's our angle theta. And we started this one by saying that x is equal to 2 sine theta. So I'll write that over here. X is equal to 2 sine theta, which gives us that x over 2 is sine theta. So sine is opposite over hypotenuse, so we have x and 2, giving us the adjacent being the square root of 4 minus x squared, right? And now that we have that, we can use that to complete this problem, all right? I'll shift this down here, but I'll shift this a little bit up, because I'm going to use that. All right, so in here, we have, well, 6 theta. We haven't solved for theta here. In here, theta is going to be sine inverse of x over 2, or arcsine, right? So here I'm going to write this as 6 arcsine of x over 2 minus 6 times sine theta. That's from the triangle. Remember, sine is opposite over hypotenuse, so I end up with x over 2, right? And cosine. Cosine is adjacent over hypotenuse, so I end up with the square root of 4 minus x squared and all of that over 2. and then plus c. At that point, let's just reduce a little bit. So we have 6 arcsine of x over 2 minus 3 halves x times radical 4 minus x squared plus c, right? And that would be the final answer. See, I knew there was something that was wrong. I'm glad we went back to fix that. Good job, everybody. Good job. All right. So that was D. Example E. So here we go. E. E has the integral from radical 3 to 2 of the square root of x squared minus 3 over x dx. All right. So here we go. So here we have a function minus a number. Because we have a function minus a number, I know that what we're going to start with is letting that function x be equal to 3 secant theta on there. Okay, so now that tells me now that dx is 3 secant theta tan theta d theta. All right, but now I also need to figure out the new values of um, of our angles, right? Of our bounds, I should be saying. All right. So let's see what happens here. From from this line, from this line, we can say, so I'll write it over here. We can say that theta is equal to x over, excuse me, not x over 3, not just like that, secant inverse of x over not 3, radical 3. Why is it radical 3? Because this is in the form of x squared minus radical 3 squared. There we go. Look at that. I caught my mistake early this time. Good job. Good job, us. We should be proud of me. But anyway, so at this point we've got, so I'll take that out of there. So that's why it's radical 3. All right. And now, so it's x over radical 3. All right. And when x is equal to radical 3, so we got to change our bounds, right? When x is equal to radical 3, well, then theta would be secant inverse of radical 3 over radical 3, which would be, well, secant inverse of 1. And from my unit circle, that happens at 0, right? Remember, secant inverse is of 1 is saying at what angle is secant equal to 1. And well, the reciprocal of secant is cosine. So it's essentially saying at what angle is cosine the reciprocal of 1. Well, I mean, the reciprocal of 1 is 1, but the point still stands that it is just at the angle of 0. Now, that's for when x is equal to radical 3. Perhaps I'll shift this over. And we need to figure out what happens when x is equal to 2. So when x is equal to 2, we get that theta is secant inverse of 2 over radical 3. All right? So let's think about that one. So what that's saying is, what is the angle such that secant of that angle is 2 over radical 3? Well, that would happen where its reciprocal, cosine, is the reciprocal of 2 over radical 3. So it happens when cosine is radical 3 over 2, which happens at the angle of pi over 6. All right. So that again, that's just from knowing the unit circle. All right. So you really need to remember your unit circle. All right. So now let's go ahead and rewrite the integral. So in here we're gonna say the integral now becomes the integral from originally radical 3, it's now 0. Originally 2, it's now pi over 6. And we have the square root of x squared, but x was radical 3 secant theta, so radical 3 secant theta squared minus 3 squared. Not 3 squared, just 3. Sorry. All of this over x. X was again radical 3 secant theta. And then dx was this entire thing. Radical 3 secant theta tan theta d theta. And let's simplify this. I see that a few things cancel each other out. Radical 3 and radical 3, secant and secant. And now what are we left with here? Well, we're going to have now the integral. Let me change the color. There we go. The integral from 0 to pi over 6 of, well, perhaps I should simplify that radical first. So let's look at that radical. I'll do it in yellow on the side over here. So we've got the square root of radical 3 secant theta squared minus 3. That's going to give us the square root of 3 times secant squared theta minus 3, which is going to be the square root of 3 times secant squared theta minus 1, giving us radical 3 times tan squared theta. And as our final result there, it would be radical 3 times tan theta. So that's what that radical becomes. So it is just radical 3 times tangent theta. But we still have this times tan theta d theta out there. So times tan theta d theta. So at this point we get the integral from 0 to pi over 6. We get the radical 3 on the outside, and on the inside we get tan squared theta d theta. All right, excuse me. So now, at this point, we're going to say, well, tan squared is secant squared theta minus 1 d theta. And taking the integral of that, we end up with, well, the integral of secant squared is just tangent theta minus the integral of 1 is just theta because we're doing this with respect to theta. And now this is from 0 to pi over 6. Now these bounds are already in terms of theta, so we don't have to worry about building the triangle anymore. All right, that's one of the beauties of changing the bounds. All right, you don't have to worry about the having to go back to the original variable, especially with these trig substitutions. So at this point, well, what do I get? I end up with radical 3 times, let's plug in pi over 6. So I have tangent of pi over 6 minus pi over 6, and that's for plugging in the top, minus radical 3 times tangent of 0 minus 0. Tangent of 0 is 0. So that means that entire thing, that entire part right there, that just goes to 0 and it goes away. So now, tangent of pi over 6. Well, if you recall what that might be on top of your head, recall that tangent is sine over cosine. Right? So we have that minus pi over 6. And then sine of pi over 6, well, that you should know from the unit circle. And sine of pi over 6 is 1/2. Cosine of pi over 6 is radical 3 over 2. And then we have that minus pi over 6. From there, I have that 1/2 divided by radical 3/2. 1/2 divided by radical 3/2. So dividing by a fraction is the same as multiplying by the reciprocal. So those cancel each other out. So I end up with just 1 over radical 3. Right? So that was this part right here. So I've got radical 3 times 1 over radical 3 minus pi over 6. All right. Um, if you really wanted to, we could distribute the radical 3, and I end up with 1 minus radical 3 pi over 6, right? And I mean, I'll leave it at that. If you really wanted to just have one fraction, we'd have 6 minus radical 3 pi, all right? All right, now there are some special integration formulas that you should recognize or be able to see why they would be useful at the very least, all right? So let's look at some of them. Well, you know what? I'm going to write them down. So these are special integration formulas. All right. So in here, I'm going to start first by writing down what they are. So if I have the integral of the square root of a squared minus u squared du, that's going to be 1/2 times a squared arcsine of u over a plus u times the square root of a squared minus u squared plus c, right? And that's an u over a there, right? And this one was a squared minus. There we go. So that's the first one. The second one has the integral of the square root of um, u squared minus a squared, right? And in here, what we end up with, so du, it would be 1/2 times u times radical u squared minus a squared ln of the absolute value of u plus the square root of u squared minus a squared plus c. All right. And the last one here, the last one says if I have the integral of the square root of u squared plus a squared, all right, du, I would get written up and get, whoa. So in here, sorry, if I have the square root of the integral of the square root of u squared plus a squared du, there we go. This will end up being 1/2 times u times the square root of u squared plus a squared plus a squared times ln of the absolute value of u plus the square root of u squared plus a squared plus c. All right. So those are the three special trig formulas. Now, you don't really have to memorize these, all right? Um, in fact, I encourage you not to memorize these. These are not easy to memorize, but what I do want you to consider is that you can come up with these on your own, all right? So let's look at that first one. Let's see why that first one is what it is. So it was the integral of the square root of a squared minus u squared du, right? Now, in here, I'm going to start by saying, well, I've got a subtraction inside a radical. So that tells me right away that u would be a sine theta, meaning that du would be a cosine theta. This also means that, well, we'll leave it as that for now. So in here, this integral becomes now the integral of the square root of a squared minus a sine theta squared du. So what I get now is the integral of the square root of a squared minus a squared sine theta, well, sine squared theta. And then, oh, hold on. Look at that. I messed up already. We need to make sure we replace everything. We need to replace the du. I completely forgot to do that. That's awful. All right, so we have a cosine theta d theta. D theta. There we And at this point, we end up with the integral of the square root of a squared, and that would be 1 minus, well, I can't factor that out just yet. Let's actually apply the square first. So I end up with a squared times sine squared theta, and then with an a cosine theta d theta. And now I can factor out an a inside that radical, so I have a squared times 1 minus sine squared theta. Still, well, that a I can bring it all the way to the front. Well, I'll leave it in C here for now. A cosine theta d theta. That radical, inside that radical, we have a 1 minus sine squared. 1 minus sine squared is just cosine squared. So I have a squared cosine squared theta. And I have an a cosine theta d theta. And at that point, well, I end up with the integral of a cosine theta times a cosine theta d theta. Okay? So what do we do there? Well, let's consider that we have a squared times the integral of cosine squared theta d theta. Alright? Now, at that point, notice that we have an even power of cosine. An even power of cosine means that we need to use the power reduction formula. So in here, the power reduction formula applied to cosine squared gives us the integral of 1 minus cosine of 2 theta over 2 d theta. So I end up with a squared over 2. By the way, throughout this whole time, a is just a constant, right? That's why I'm able to pull it out and treat it as if it was just a number. So a squared over 2 times the integral of 1 minus cosine of 2 theta d theta. And integrating that, well, I end up with a squared over 2 times the integral of 1 with respect to theta is just theta. The integral of cosine was going to be sine, but I'm going to divide this over 2 because of the argument there. And then that plus c. The next thing I'm going to do here is I'm going to say that sine of 2 theta is 2 sine theta cosine theta. And we have that over 2 plus c. Those over 2's, notice that they cancel each other out. Alright? But now, the problem wasn't about theta, it was about u. So let's make sure that we put it back into terms of u. So we have, oh, look at that, finally a problem that was about u. But anyway, in here, u is equal to a sine theta, right? So u is equal to a sine theta, which tells us that u over a is equal to sine theta. At this point, this gives me the triangle that if this is theta, well, from SOHCAHTOA, we have opposite over hypotenuse, opposite over hypotenuse. The adjacent side would be the square root of u squared minus a squared, right? So now, the other thing that this tells me from this line is that theta is equal to sine inverse of u over a. So at that point, well, what do we have? We're going to write this as a squared over 2 times, well, theta was sine inverse, right? So theta is sine inverse. So we have here sine inverse of u over a, right? And then minus sine theta from SOHCAHTOA, sine is opposite over hypotenuse. Um, Hold on, I just realized I made another mistake. How awful of me with all these mistakes on this video. What a jerk. That's okay. So this is a plus. This is a plus. Because cosine, the formula is plus, not minus. For sine, it's minus. For cosine, it's plus. Alright? So there we go. Fix that. And this plus. Alright. Now that I noticed that, we continue back to our regularly scheduled programming. So, in here, sine theta, opposite over hypotenuse. So, u over a. Cosine theta, adjacent over hypotenuse. So, the square root of u squared minus a squared over a. And then all of this plus c. If I distribute just the a squared, not the 2, just the a squared, I end up with 1/2 times a sine inverse of u over a plus the a squared. Look at this. This is an a squared on the bottom down here, right? Because we have a times a. So this a squared cancels out both of those. So I end up with u times the square root of u squared minus a squared. And again, these two got canceled out by that. And then we have this plus c. And look at that. That is the actual formula that we had up here, that first formula. All right. So you don't really need to memorize these. You can derive them on your own. All right. Um. All right. So that is the end of 8.4. Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.